All right, buckle up because we're going to be diving into negative time.
Yeah, negative time.
It sounds like something out of science fiction.
It does sound a little paradoxical, but it is actually rooted in real quantum physics experiments. So we're talking about photons, right?
Okay.
Those tiny little particles of light seemingly traveling through time in reverse.
Hold on. Reverse time travel. I'm not buying it.
It's real.
Is this like theoretical physics or is this an actual thing?
It's real. Scientists at the University of Toronto have been conducting these just mind-boggling experiments with photons and rubidium atoms cooled to ultra-low temperatures.
Oh, wow.
What they've observed is photons exiting these atom clouds before the atoms even have a chance to release the energy they absorbed from the photons.
So the photons are leaving before they even enter.
Think of it this way. In the quantum world, things aren't as clear-cut as our everyday experience.
Yeah.
It's all about probabilities. With particles existing in multiple states at once.
Multiple states at once. So like a photon can be both inside and outside the atom cloud.
Essentially, yes.
Okay.
It's like a car entering a tunnel.
Yeah.
We see it go in, then come out, right?
Yeah.
But in the quantum world, that car could be both in and out of the tunnel at the same time.
Okay, so are we saying photons are literally traveling back in time?
No. No, we're not talking about building a time machine.
Okay, got it.
What we're seeing is time behaving very differently at the quantum level.
Okay.
It challenges our understanding of the order of events. This negative time effect suggests that at a microscopic level, the cause and effect sequence that we're used to can get scrambled.
So cause and effect can get fuzzy. So is our understanding of time just totally wrong then?
It doesn't mean our everyday experience of time is wrong, but it does point to a much more complex picture of time than we might initially grasp. Think of it this way. These quantum experiments are revealing new layers of reality, a reality where time can behave in ways that seem paradoxical to us.
Okay, so we're not talking about time travel.
Right.
But then what's the big deal with negative time? Like, why should we care?
Because it challenges our most fundamental assumptions about the universe.
Like what?
It suggests that time itself might be a lot more fluid and malleable than we ever imagined, especially at the quantum level.
Okay.
And if time can behave so strangely at the quantum level, what other bizarre phenomena might we uncover as we delve deeper into this realm?
So you're saying this research might have far-reaching implications? But if we're talking about photons, right?
Yeah.
Like particles of light, wouldn't that mean that they're breaking the speed limit? The speed of light?
That's a great question, and it's important to emphasize that these photons aren't actually carrying information faster than light.
Okay.
We're not talking about messages or signals being sent back in time. What's intriguing here is the very nature of quantum measurement and how time plays a different role at that level.
So no time travel?
No.
No breaking the cosmic speed limit?
No.
What about the laws of physics? Are we breaking the laws of physics with this negative time?
The beauty of it is that we're not breaking any laws of physics. What we're doing is refining our understanding of them. These findings are not about rewriting physics textbooks, but about expanding our view of the universe and the intricate dance of time within it.
So the universe is a lot stranger than we thought. How did scientists even stumble upon this whole negative time phenomenon?
Yeah, you're right. It does sound like science fiction.
Yeah.
But the reality is often stranger than fiction. These experiments are pushing the boundaries of what we thought was possible, showing us that time can act in ways that seem to defy logic.
Okay, so how did they measure this negative time? Did they invent some sort of quantum stopwatch or something?
They essentially used the rubidium atoms themselves as incredibly sensitive clocks. By precisely measuring the time it takes for the photons to interact with these atoms, they were able to observe this curious phenomenon of photons exiting before they seem to fully enter.
So they're using atoms as clocks to measure time at the quantum level.
It is, and what these clocks are showing is that our everyday understanding of cause and effect, where the cause always precedes the effect, might not be as straightforward as we once thought, especially in the bizarre world of quantum mechanics.
Okay, so I think I'm starting to get this, but my brain is definitely doing somersaults right now.
It's a mind-bending concept, that's for sure. But it's precisely this kind of research that forces us to reevaluate our basic assumptions about the universe and embrace the fact that there's still so much out there that we don't understand.
So while we're not booking tickets for time travel just yet, this research into negative time is a stark reminder that there are still mysteries in the universe that can turn our world upside down.
Absolutely.
Yeah.
And who knows what other counterintuitive phenomena might be lurking out there, just waiting for us to uncover them. Maybe one day we'll even have to rethink our definition of time itself.
Well, that's a thought for another day. I think I need a moment to process all of this.
Take your time. It's not every day that we get to explore the boundaries of time itself.
You're telling me. But before we get too lost in the quantum rabbit hole, let's take a step back and review the experiment itself.
Sure.
Can you walk us through, what exactly do they do and what exactly do they find?
Sure. Imagine these ultra-cold rubidium atoms as a sort of quantum playground for photons.
Okay.
Researchers use lasers to excite these atoms, putting them into a higher energy state.
Okay.
Then they sent photons through this cloud of excited atoms.
So the photons are interacting with these excited atoms.
Yes.
And then what happens?
That's where things get really interesting. They measured how long the rubidium atoms stayed in that excited state after absorbing the photons.
Right.
What they found was that sometimes the photons were exiting the cloud before the rubidium atoms returned to their ground state.
Wait, hold on. They're leaving before they even arrive. How's that even possible?
It's not that they're literally traveling backwards in time.
Okay.
It's more about the fact that in quantum mechanics, things don't happen in a neat linear sequence like they do in our everyday experience.
Okay, so you're saying at the quantum level, the order of events can get a little fuzzy.
Exactly. It's like watching a movie where the ending scene plays before the beginning. It challenges our intuitive notion of cause and effect.
So cause and effect don't always apply in the quantum world. This research wasn't about time travel, was it?
Precisely. It wasn't about building a time machine. Yeah. It was about probing the fundamental nature of time itself. Okay. Especially at the tiniest levels of reality.
Okay, but if we're talking about photons, like particles of light,
right?
Doesn't this mean they're moving faster than the speed of light, like Einstein said was impossible?
That's a great question, and it's important to clarify that these photons aren't actually transmitting information faster than light.
Okay.
They're not carrying any messages or signals.
Okay.
What we're seeing is more about the strange nature of quantum measurement and how time behaves differently at that level.
Okay, so no time travel.
Right.
No breaking the speed limit.
No.
But then what's the big deal about this negative time? Why should we care?
What's fascinating here is that it points to a deeper truth about the universe, that the reality we experience in our everyday lives with its linear progression of time is just one very specific way that time can manifest.
Yeah.
There are other possibilities, other ways that time can behave, particularly at the quantum level.
Okay.
And these experiments are giving us a glimpse into that mind-boggling realm.
So what you're saying is that these results could have significant implications,
yeah,
like for our understanding of physics as a whole.
It is. These findings don't mean we need to rewrite all the physics textbooks just yet. However, they do suggest that there are still mysteries in the universe that defy our common sense and intuition.
This whole negative time idea, it stirred up quite a bit of debate in the scientific community, hasn't it?
It has. Not everyone agrees on the interpretation of these results.
Okay.
Some physicists argue that the term negative time is misleading, that what's being observed is more about phase shifts in the photon's path rather than a true reversal of time.
So where do you stand on this?
I believe this research is incredibly valuable, regardless of how we interpret the results. These experiments are forcing us to confront the limitations of our understanding of time and the truly bizarre nature of the quantum world. I'm definitely feeling a bit mind blown. So while we're not booking tickets for time travel just yet, this research into negative time is a potent reminder that there are still many mysteries of the universe waiting to be unraveled. Absolutely. And who knows what other counterintuitive phenomena might be lurking out there, just waiting for us to discover them.
I'm excited to see what the future holds for our understanding of time and the quantum world. It seems like we're just scratching the surface of something truly profound.
I completely agree, and who knows? Maybe one day we'll even figure out how to build that time machine. After all,
One can only hope.
it's fascinating, isn't it? You know, for years, physicists have been aware of this phenomenon, right? Where light appears to exit a material before it even enters, but it was largely ignored.
Ignored? Why would they just ignore something like that? Sounds pretty important to me.
Well, you know, they attributed it to the way light waves distort as they interact with matter.
Okay.
So essentially, they dismissed it as an illusion, like a trick of the light, rather than a true reflection of what was happening at the quantum level.
They just thought it was a visual quirk, right? Like one of those optical illusions, where like a straight line appears bent or whatever.
Precisely.
Yeah.
But these new experiments are challenging that assumption.
Yeah.
They suggest that something far stranger is occurring.
Okay.
That time itself might be behaving differently in the quantum realm.
Okay, so if the photons are exiting before they enter, does that mean they're traveling backward in time?
It's not about time travel in the conventional sense. It's more about recognizing that in quantum mechanics, events don't unfold in a neat linear sequence. Like our everyday experience.
Yeah,
right.
So you're saying the photons aren't actually going back in time; they're messing with our perception of cause and effect.
Exactly. It's like the photons are experiencing time in a way that we can't fully comprehend.
Okay.
Their behavior is governed by the rules of quantum mechanics, which are vastly different from the classical physics that govern our macroscopic world.
It's mind-boggling to think that there might be like a whole other set of rules governing the universe at the quantum level. It makes you wonder what other weird things are happening out there that we just haven't even thought about,
Absolutely. That's what makes quantum physics so captivating. It constantly reminds us that the universe is far more mysterious and complex than we currently understand.
Right.
It challenges us to question our most fundamental assumptions about reality.
So this negative time phenomenon, we're not talking about building a time machine, right?
No, this isn't about building a time machine.
Okay, good.
It's about delving into the very, very nature of time itself. Understanding how time behaves at the most fundamental level in the realm of quantum particles.
Okay.
And what we're learning is that it's far weirder and more complex than we ever imagined.
I've heard some physicists say this whole negative time thing is just a matter of perspective.
Right.
Like it's not really like time going backwards, but just like a different way of interpreting what's happening.
It's a valid point.
Yeah.
There's certainly a lot of debate in the scientific community about how to interpret these results.
Yeah.
But what's important is that these experiments are pushing us to ask deeper questions about time and how it works.
Even if it's not literal time travel, just the fact that we're seeing these effects at all is pretty mind-blowing, right?
Absolutely. It's a testament to human ingenuity.
Yeah.
And our insatiable curiosity to understand the universe, even when it leads us to the most bewildering aspects of reality.
So where do we go from here? What are the next steps in this research?
Well, one of the most crucial steps is to replicate these experiments.
Okay.
Right, and verify the results. We need to ensure that what we're observing is a genuine phenomenon and not some kind of experimental error. And
if the results hold up, what are the implications? Even if we never figure out time travel,
the implications are potentially enormous.
Yeah.
A deeper understanding of time could revolutionize our understanding of physics, cosmology, and even the very nature of reality itself.
That's pretty huge. But for now, I'm content with the fact that we've at least gotten a glimpse behind the curtain of time and witnessed something truly extraordinary.
I agree. And who knows what other wonders await us as we continue to explore the strange and beautiful world of quantum physics.
Yeah.
Perhaps this is just the tip of the iceberg.
Right.
And there are even more mind-bending discoveries yet to be to be made.
It's both exhilarating and a little terrifying to think about.
It is, but that's the beauty of science.
Yeah.
It's about embracing the unknown, challenging our preconceived notions, and constantly expanding our understanding of the universe and our place within it. And who knows, maybe one day we'll even unlock the secrets of time travel. But until then, we have a lot of exploring to do.
It's like we're trying to understand a game where the rules change every time you look away.
Yeah, like a game where the players can be in several places at the same time.
Right, and the ball somehow crosses the goal line before it's even kicked.
Exactly.
It's our everyday intuition just can't keep up.
No, it can't. It demands a whole new set of tools and concepts.
Yeah. So how do scientists even measure this negative time? It sounds like something out of science fiction.
Well, they use lasers to excite the rubidium atoms.
Okay.
And then they very, very precisely measure the time it takes for the photons to interact with them.
Okay.
They're essentially using the atoms as these incredibly sensitive clocks.
So these atomic clocks are telling us that sometimes the effect, the photon exiting the atom, happens before the cause, like the photon entering the atom.
It's wild to think about.
So are there any practical applications for all this? I mean, even if we can't build time machines, could this lead to new technologies?
The possibilities are certainly intriguing. It's still early, but this research could have implications for things like quantum computing.
Oh wow!
Secure communications, even our understanding of the very early universe.
I'll definitely be keeping an eye on this.
Yeah, it seems like we're just, at the beginning of a very, very exciting journey into the mysteries of time.
Well, that's our deep dive into negative time. We explore the strange realm of quantum mechanics where time itself seems to bend and twist.
Thanks for listening. And remember, the universe is full of surprises.
It sure is.